We've now built up the machinery that we can begin asking some really interesting questions about reactions that don't necessarily involve them being at equilibrium. And that's what we're going to cover in this current video about the spontaneous direction of reactions. So our learning goal is to use the reaction quotient to determine the spontaneous direction. That is to say, we're going to have some mixture of reaction species thrown together, and it could include both reactants and products. If it's not at equilibrium, the question is, can we predict which direction it's going to go? Is it going to go back toward the reactants or forward toward the products? So we're going to introduce something I'll call the reaction quotient test. Now we know that at equilibrium, the reaction quotient is equal to the equilibrium constant. That's how we got the equilibrium constant in the first place. Now, what if the mixture, though, has a different value for the reaction quotient? That is to say, it's not equal to the equilibrium constant. Well, remember that the reaction quotient is, simply stated, it's the concentrations of the products divided by the concentrations of the reactants. Now, there may be some other exponents thrown in there, but that's basically what it is. So we only have a couple of possibilities. One possibility is that the reaction quotient happens to be larger than the equilibrium constant. So what does that mean? Okay, if QC is too large, what is that telling us? Well, it's telling us that the thing that's in the numerator, namely the products, are too large. And if they're too large, then in order for this reaction mixture to go toward equilibrium, we're going to have to reduce those products by converting some of them back into reactants. So we're going to have to do the reversed direction of the reaction. On the other hand, if the reaction quotient is too small, if it's less than the equilibrium constant, then that tells us that the numerator is not large enough. Okay, the denominator is too large, but the numerator is too small. So in order for us to adjust and reach equilibrium, we're going to have to increase the products again. We're going to have to move the reaction forward. Right? If you've got that down, you pretty much have this concept sewed up. But let's look a little bit more and see how we can actually get some other information out of this. Now, I want to introduce the equilibrium constant as basically just being a point on a number line. Now, our own number line for this, though, starts at 0 and it goes positive. And that's just a reflection of the fact that the equilibrium constant can't be a negative number. Okay, it's a function of a bunch of positive quantities, the reaction concentrations, so it can never be less than 0. It can only be greater than 0, and that's true of the reaction quotient as well. So this limits our field of our range of motion here. Now, the other thing I'm going to point out is that the reaction, wherever the reaction quotient happens to be, the reaction is going to have to proceed in the direction from where QC is to where KC is. KC doesn't change. That's why it's called the equilibrium constant. It stays in the same place. So let me illustrate this. So for example, let's suppose that our reaction quotient is down here somewhere. So this really implicitly means that the reaction quotient is less than the equilibrium constant. It has to move toward the equilibrium constant to reach equilibrium, so it's got to move in that direction. On the other hand, if the reaction quotient is up there, it's above Kc, then it's greater than the equilibrium constant. It would need to move back in that direction. Now, the interesting thing about this is if we look at the greater thans and less than signs there, they are pointing in the direction that the reaction has to proceed. So if we put K first and Q second, in alphabetical order, then the greater than or less than sign tells us whether we have to move to the right or to the left in order to achieve equilibrium. So Kc greater than Qc means reaction proceeds to the right toward products. Kc less than Qc, reaction has to go to the left toward reactants. And lest I forget, there's another case, and that is when Kc equals Qc, and then the reaction is equilibrium and it doesn't go anywhere. So let's look at an example. This is a fancy organic reaction, sodium formate with glycolic acid to form formic acid and sodium glycolate. For what it's worth, formic acid is the sting in ants. It's the stuff that gives ant sting a sting, and sodium glycolate is a hair remover. So, some of you may have used that before if you've ever used any hair remover. So we're going to start with some initial concentrations for each of these things. And we're also told that the equilibrium constant for this reaction is 0.83. So the question is, these concentrations, which direction will the reaction go if we start with these concentrations? So which direction will this mixture proceed? Okay, this is actually very easy to figure out because we just have to calculate the reaction quotient. So here is the expression for the reaction quotient. It's the product of the concentrations of the products divided by the product of the concentrations of the reactants. And when we plug all those numbers in, we find that the result is that the QC is equal to 0.77. So if we compare this to the equilibrium constant, we find that 0.83 is greater than 0.77. So this tells us the reaction must proceed to the right in order to achieve equilibrium.